Hi there, it's David Giltfand again, and in this video we're talking about Schlieren imaging. In this course we've made frequent use of an imaging technique called Schlieren imaging. This technique is used to visualise compressible flow features such as shock and expansion waves, which are present in our flow but which normally we can't see with the naked eye. Schlieren is a long-established optical technique which visualises density changes through a flow field. Here is an example of a Schlieren image used in this course. The black silhouette image is a scramjet intake. Flow is from right to left, and we can see upper and lower shock waves form around the leading edge. We can also see boundary layers along the surface of the intake. A single image such as this one can be used to validate our shockwave theory and demonstrate phenomena such as flow viscosity, which we would never be able to see with the naked eye. As we noted earlier, we can't normally see shock waves through our flow. Schlieren imaging reveals these compressible flow features. However, these do not look like normal photographs. We only see a silhouette of our model. However, other features can suddenly be seen in vivid detail, such as shock waves. In this module, we're going to examine the Schlieren technique in more detail and show you how Schlieren images are generated, in order to bring some physical meaning to these images. Generating a Schlieren image requires three elements. We need an appropriate wind tunnel to generate a test flow, and for hypersonic flight speeds this means we need an impulse facility. We need to obtain or manufacture a test model or test specimen to pass our test flow over. Finally, we need a suitable Schlieren optical setup. So this involves optical elements, such as lenses and mirrors, an imaging device, such as a high-speed camera, and appropriate instrumentation, triggering, and data acquisition hardware. So first we'll consider the impulse wind tunnel. For these experiments we are using one of UQ's reflected shock tunnels called the Drummond tunnel. Compared to our other facilities, this is a relatively small facility, approximately 6 meters in length. The facility can produce a 2 kilometer per second test flow, so that's approximately 7,000 kilometers an hour, for about 1 millisecond. The size of our core flow, which is the region of steady flow available to test our model, is about 60 millimeters in diameter. Here is a schematic of the Drummond tunnel. We'll shortly examine its operation, but first we will highlight some important parts of its hardware. At the upstream end, we have a high-pressure helium driver. So this is basically just a tube which is filled to about 3.5 megapascals with pure helium gas. Now separating this tube from the rest of the facility is a 0.5 millimeter thick aluminium primary diaphragm. And this diaphragm forms a sealed closed compartment for the helium. The rest of the tube between the aluminium diaphragm and the nozzle at the other end, that's the nozzle here, the rest of the tube is sealed off and is initially filled with air, and this is called the shock tube. For the test shown in this course, the shock tube is initially filled with 17 kilopascals of air, so that's about a fifth of atmospheric pressure. One important strength of impulse facilities is that this shock tube doesn't need to be filled with just air. So we can fill it with any test gas, and in this way we can simulate flight through other atmospheres with relative ease. And that's something that's not possible with a normal fan-driven wind tunnel. Now, to seal the shock tube from the nozzle in the test section, we use a thin mylar secondary diaphragm. Mylar is a type of plastic. And then the rest of the facility comprises a test section and a large dump tank. And these are initially pumped down to a vacuum. Since our test gas is usually at relatively low pressure, and the test section and dump tank are also at low pressure, we only need a very thin secondary diaphragm to support the small pressure differential. And this here is what the actual Drummond tunnel hardware looks like. So in the next few slides we'll examine how the facility works. As we saw earlier, the facility is initially compartmentalized using two diaphragms. One here and one here. On the left, we have high pressure helium, initially at 3.5 megapascals or 35 times atmospheric pressure. So that's the red volume of gas. To contain the helium, we use a 0.5 millimeter thick aluminium diaphragm. So that is across this interface here. The rest of the tube is filled with low pressure air. The initial pressure ratio between the 3.5 megapascals of helium and 17 kilopascals of air is over 200 times. The downstream end of the shock tube on the right hand side, here, is essentially a closed tube except for a small opening at the end. To prevent the air in the shock tube leaking through this small opening, we use our thin mylar or plastic diaphragm, and this is just strong enough to keep the tube sealed. Downstream of the shock tube we have a nozzle which opens up to the test section, and we place our model here. The test section and dump tank form a large volume which is initially held close to vacuum. To operate the facility, an internal spike is used to rupture the aluminium diaphragm. When the barrier between the high pressure helium and the low pressure air is removed, the helium forcefully expands towards the test gas. Now we use a light gas such as helium because it can discharge its energy very rapidly by virtue of its high sound speed. With a pressure ratio over 200 times and a very high sound speed compared to the air test gas, the helium drives a strong shock into the test gas. For this reason, we call the helium gas our driver gas. As time progresses, the helium, which undergoes an unsteady expansion, flows towards the test section, driving a shock through the test gas. The test gas is processed by the shock wave. This compressively heats the test gas, raising its pressure and temperature, and it accelerates the test gas in the direction of the test section. Pay attention to the progress of the driver gas and test gas during these slides. So we have the driver gas here, and the test gas. Except for the small opening where the nozzle begins, the shock tube is a closed tube on the right hand side. All of the test gas flowing towards the test section is brought to a halt when it hits the end of the tube. The mechanism for stagnating the gas is a reflected shock wave. When the test gas, which was already hot and at high pressure, is then stagnated, its kinetic energy is converted to heat and pressure. It was originally at 17 kilopascals, it's now at 2.3 megapascals. And it was originally at room temperature, and now it's nearly 2000 Kelvin. Remembering that we only have a thin secondary diaphragm, only strong enough to resist a fraction of an atmosphere of pressure, when the test gas stagnates at the end of the tube, the diaphragm is almost instantaneously obliterated. The shock tube is no longer sealed off from the nozzle and test section. The hot, high-pressure air at the nozzle inlet, which we call the stagnation region or nozzle supply region, begins to expand through the nozzle. When the test gas reaches the nozzle exit, it has undergone an isentropic expansion which has converted its pressure and heat energy into velocity. When the gas arrives at our model, our test time begins. During the test time, the model will feel like it's flying through a hypersonic flow. For the Mach 7 flow condition we're commonly used in this course, this corresponds to a flight speed of about 2 kilometers per second, a static temperature of 210 Kelvin, a static pressure of 586 pascals, and a Mach number of 6.8. So this is equivalent to flying at about 2 kilometers per second at an altitude of about 35 kilometers. Now the facility continues to drive air test gas over the model until eventually the driver gas arrives. When the helium driver gas eventually passes over the model, the useful test time has definitely ended. But usually the test time ends a little bit before this point, since the test gas flow properties begin to diverge from the target condition sometime earlier. In the Drummond tunnel, the period of useful, steady test time is about 1 millisecond. The second requirement for Schlieren testing is that we need a model. In this example, that model is a scramjet intake. So where does it go in the facility? It's located in the test section. So here we have the nozzle, here we have the model. Test gas will flow from the nozzle over the model in the direction shown by the arrows. Finally, we require a Schlieren system. We first need to take a light source and collimate the light. This light is then passed through our test section and focused back to a point. Any of the collimated light which passed through density gradients in our test section, they might be shock waves or expansions, that light will be refracted. The refracted light will then be deflected from the focus point. So here we can see light passing through a region of changing density. Here we have a simple Schlieren setup. On the left we have a point light source. Then using a lens or concave mirror, we can collimate the light and pass this column of light through our test section where the model is located. Now note, in the actual experiment, the collimated light is passed through the windows and is travelling perpendicular to the flow. So it would be coming out of the screen in this case. A second lens or mirror focuses the light back to a point, and a knife edge is located just next to this focus point. So that knife edge is here. The image finally is captured by the camera. As noted, we locate a knife edge at the point of focus. With this arrangement, collimated light, which is refracted as it passes through our hypersonic flow field, will be deflected and won't pass through the focus point. Light deflected towards the knife edge will be cut off and will not continue to the camera. Light deflected away from the knife edge will still reach the camera. As a result, regions of density change in our flow, which have refracted our collimated light, will appear lighter or darker on our image. So here are some results. Considering our scramjet intake in the test section, in these images, flow is travelling from left to right. Two separate Schlieren images have been taken in order to cover the full field of the view. We can now see compressible flow features with considerable detail. We'll conclude this section with a video of an actual Schlieren experiment. Our experimenter is Yassine Abdelmajid, and he's a UQ student and research assistant who has used UQ's Drummond tunnel to produce much of the Schlieren shown in this hypersonics course. After studying this module, we hope you'll have a better understanding of Schlieren imaging and a better feel for what these images physically represent.
Hi, my name is Yassine. I'm a summer research scholar with the University of Queensland's Hypersonics Division. Today I'm going to be doing the turnaround for the Drummond tunnel, which I have behind me, and that will involve the changing of the diaphragms and the pumping down to a vacuum. First we have to turn around the tunnel. This involves changing the diaphragms and pumping down the facility to a vacuum of around 2.5 to 3 torr. That's millimeters mercury. Here I am inserting a new aluminium diaphragm to the driver. Next we check that the Schlieren system is working. To do this, I blow a heat gun across the optical path which causes density gradients, and this will show up on our computer. We then fill the required driver and test gases in the facility. We arm our instrumentation so it will trigger when the experiment takes place. Now we fire the facility. And finally we can review our experimental results. This includes both the Schlieren and the results from the oscilloscopes and sensors.